So we've established that geometric optics depends on light traveling in a straight line, which is accurate, but we often talk about light being bent as it enters materials. So the question is, how does that work? And it works because light travels at different speeds in different materials. So the speed of light is basically 3 times 10 to the 8 meters per second. But in different materials, the effective speed slows down. And that slowing down we describe by the index of refraction. So N is our index of refraction. And it tells us how much off this vacuum speed we have. So we use N equals 1 for a vacuum, or usually we say that's also the case for air. So we then say the speed of light V is given by the speed of light in a vacuum, C, divided by the index of refraction. So the index of refraction is always going to be bigger than 1 because we're going to be going slower than the vacuum speed of light. So N is equal to, you can rewrite this of course, C over V if you like. It's the amount of the speed of light that we're going, right? And so for water, for example, just to give you values and why this is useful, because the light's still going pretty fast. So for water, the index of refraction is about 1.33. For glass, it varies the types of glass, but the index of refraction is about 1.5. And notice there are no units because it's a speed over a speed. It's just the speed of light in a vacuum is 1.5 times faster than it is in glass. And so then the way this manifests itself is that we can think of, this is one way to sort of think about it. If you're starting from a point up here and you're going, for example, from a parking lot where it's hard pavement over on the sand to this spot over here where you want to set up your towel on the beach. So this is sandy, right? And you can't run as fast, right? We've got a straight line distance. Whoa, that's not a straight line distance. We're moving our beach spot. That's our straight line distance. But we actually can't get there. If we think about trying to get from this spot where we had to park to where we wanted to set up our beach towel, we wouldn't probably take the straight line distance because we'd be so much longer in the sand, especially if we're pulling a lot of things. So we would tend to take a distance, take a path that says, let's go further. We'll walk a little bit further, but we'll be able to go faster because we can walk more easily along the parking lot than along the sand. And so light takes this same approach. It takes sort of the least amount of time passed. So if we want to talk about light getting from here to here, this is a good analogy for what happens. And so we describe what happens if we think about, we change this from parking lot now to air or a vacuum, and we say this isn't something sandy, we say this is, say, water or glass, then the path that the light takes is this pink path that we have right here. And we can describe this in terms of the index of refraction. And so we set up a normal to our surface, something that's perpendicular, and we say this is our angle in, or the angle of air, and this is the angle that's refracted. Often angle refracted, so angle incident, angle refracted. Then we can say there's a rule that we can derive with the equations, with Maxwell's equations, but we're not going to, that tells us the relationship between these angles, and it says N of the upper material, we'll say air, times sine of the theta A, so I'm going to call this theta A because I think it's easier just to associate the theta with the material, is equal to N of water sine theta water. Okay, and so that is, in fact, We're going to call this theta water. That's our relationship. And so that tells us how these angles shift. So notice when you have a bigger index of refraction, we need a smaller angle to have the same equality. So that's why this shifts towards the normal. And these angles are always measured relative to the normal, to the surface interface. Okay, so that's how we understand refraction, and it's the bending of light, what looks like the bending of light, because if we're standing out here, then we can say, hey, we think that, or actually, yeah, we're standing here and we're looking what's coming on. If we see something like this underwater, say this is now a fish, oh, that's a lovely fish, then what we say from the point of view of us looking in the water is that the water followed on a straight line, and so all of a sudden it looks like this fish lives at a much shallower depth, right? And so you've seen this effect probably when you've put paddles in the water. It looks like the paddle is bent because it hits the water and sort of looks like it's shallower, or you can misjudge, especially in very clear water, you can misjudge the depth and think it's much shallower than it is because of this. We see light as traveling in a straight line. So from our point of view, whatever light that bounced off of this fish and then came back into our eyes, right, that followed this path. But from our eyes' point of view, we think it came from this straight line. Okay, so this is sort of a summary of Snell's law that says the index of refraction in one material times the angle is equal to the index of refraction times sine of the angle in the other material. And this is a drawing where the index of refraction of the second material 2 is bigger than the index of refraction of material 1. So if we look at this sort of going the other way, we can see that as we go from a material of a high index of refraction, as light goes, and then goes out along this angle, we could, in fact, as we make this angle bigger, so this becomes our new theta 2, then this is going to be our new sort of theta 1. There is a point at which we can set theta 2 so that we sort of reach a maximum, right? The maximum so that theta 1 goes to 90 degrees, right? Because as we keep increasing this, we're going to keep tilting this line further and further down. And so we can get to this point that theta 1 equals 90. And if we go beyond that, so if we make it so much bigger, so here's my theta 2, if we go beyond the point where it's 90, then what happens is we get reflection. Okay, so we get something called total internal reflection. Internal reflection. And so that is once we are beyond this so-called critical angle. And the critical angle in this case would be when theta 1 is equal to 90 degrees, then theta 2 is at its critical angle for these two materials. And this only happens if we're going from a bigger to a smaller. So we go from a bigger to a smaller. Then we get this internal reflection. And so what the critical angle for N2 sine theta critical is whatever N1 is times sine of 90 degrees, and of course sine of 90 degrees is 1, or the critical angle for this interface of object 2 and object 1 is N1 over in 2. And you can find your critical angle depending on, for example, an air-water interface or an air-glass interface is fairly common. And this is really important because if you have these glancing angles, then you can set things up so that light actually gets reflected and it gets completely reflected. And so we use glass. So we set up glass like this. You get a tube of glass, for example, and we send light coming in at a fairly glancing angle like this, such that if this is air, this is not really the way it's done. It's more complicated than just glass and air. There's something called a cladding around this. Then I can set this up so that I can have light going along this tube, and I get what's called a light pipe or an optical fiber. So fiber optics depend on total internal reflection like this. And instead of air, we usually have a material right here. That's the right index of refraction, actually several layers of it in what's called our cladding around our optical fibers. But it's got to be a lower index of refraction than the glass so that we continue to have this internal total internal reflection, and the light just keeps traveling down the optical fibers. And we try to set things up in such a way that the cladding is a good match so we don't lose any signal. We do have a little absorption, so often we have to put repeaters in the line, but in general, this is what makes all of our communications network is now built on signals of light traveling through optical fibers. And so this idea of a wire of light, basically, very thin pieces of strands of glass that are actually light wires is really important, not only in our communications, but also in all kinds of medical applications, right? All of the laparoscopic procedures all depend on light from inside of us showing up through these light fibers for doctors to see what's going on.